welcome to a factoring review meant for Algebra 1 students, although I think a lot of Algebra 2 students or even above could possibly use this as a way to get back in the swing of things as they start factoring in those classes as well. So when we're asked to factor something, we're being asked to split it into things that multiply together to get it. And whenever we first start doing that, we do that with numbers. So you can factor things like the number 24. And you can say, well, that's 2 times 12. Or you can say that's 3 times 8. Or you can say, well, that's 2 times 2 times 2 times 3. And so there's lots of ways of factoring numbers. There's ways of thinking of it. But this last way where we broke it up as much as we possibly could is essentially what we're trying to do with polynomials. We want to break them up as much as we can so that anything that has something in common that we could take out, we do. Any trinomials that we could split up, we try to. We don't leave anything unfactored that could be factored. And so this creates an issue once you've learned all the different kinds of approaches to factoring, because it can be difficult until you have more practice to know which type you're supposed to be using. So there's actually a method or flowchart kind of thing that you can use in order to be able to figure it out. And it starts with the idea of always checking for a greatest common factor, because if there is a greatest common factor, the whole problem will be easier if you take that greatest common factor out at the beginning instead of figuring that out later and trying to edit what you've got at the end and take it out. It's not impossible, but especially if you're in Algebra 1, you will find it way easier to take it out first and then look later. Once that's out, then you look at, if there is a greatest common factor, you'd look at what's inside the parentheses for this next part. If there's not a greatest common factor, you're just looking at your polynomial, and you're going to decide what to do based on how many terms there are. If there are 2 terms, there's only one way to factor it other than greatest common factor, which is the difference of 2 squares. I don't know if I can write on this in this way, but I'm gonna try. Yes, okay, the difference of 2 squares is where you have something like x squared minus 9. Both of these are squares. X squared and 9 would be 3 squared, so we can split that up into x plus 3 and x minus 3. So that's the difference of 2 squares. That's the only thing that works for this. If it is x squared plus 25, that's not the difference of 2 squares, that's the sum of 2 squares. That can't factor. If it was x squared minus 10, that doesn't factor either. So if you're in pre-calculus, you could technically get smart alecky and say that you can factor, but it doesn't factor into nice factors, kind of like how we could factor numbers into things with fractions, and we don't want to do that. Same situation here. This doesn't factor into something nice, so that doesn't work because 10 doesn't have a square root. If there are 3 terms, that's really the issue. So let's go to 4 terms. If there's 4 terms, then the only option is factoring by grouping, and so that's the one where you have 4 terms, and so you group these 2 together and look at what they have in common. You group these 2 together to see what they have in common, and then you take out that thing that's in common. And we'll do a couple of those, so I don't really feel like I necessarily need to do that all the way through right now. When there are 3 terms, what you do basically depends on whether or not it's x squared or something x squared. That's supposed to be, let's put an a there so it doesn't look like a minus. If it's just a regular x squared, that's where you're just using the trick of what multiplies to get the last number and adds to get the middle number. And splitting it just straight into 2 parentheses with an x and an x. And so those are the nice problems, those are the easy problems, but after you learn the more complicated ones, it's easy to forget that it was once so easy. It's when there's something in front of x squared that we couldn't factor out of everything that we have an issue, and we start using methods like the box method, or you may have heard of slide and divide, or split the middle term, or some other way of doing that. Because if it's ax squared, you have to split it up so that maybe it's ax and x, or maybe a can be split into two different numbers. And you basically, if you're guessing and checking, have to check all these different possibilities to see if it works. And so I'm going to show off the box method in this video. There is another pattern here, the perfect square trinomial pattern, that, like in our two-term pattern, if we have two things that square root on the outside, and in the middle we have, it has to work out that it's the square root of this and the square root of this, which is 3x and 2. Multiply those together and get 6x. This has to be double that in order for this pattern to work. And if that is the case, then it factors into 3x plus 2 squared. Or if this was a minus in the middle, it would factor into having a minus in the middle here. So that's kind of an overview of how we decide which way to factor based on what we have. So essentially, the easy thing is 2 terms or 4 terms, because there's only one option basically on both of those. 3 terms is where you just have to think what is in front of x squared, because if there's nothing, you just use what multiplies and what adds. If there's something in front of a, if it's a square root, try using the perfect square trinomial pattern if you remember it. If not, use whatever method you want to, like box method or guess and check, to split it up. Alright, now let's look at this lovely review that I've got here. It's going to take us through each of these, and it's also going to take us through solving. So if it just says factor, then our end answer should look like a multiplication problem that when we multiply it out using the rules for multiplying polynomials like the distributive property and FOIL, when we multiply it out, it should give us what we started with. So 1 and 2 here say factor the common factor out of each expression. And so each of these numbers has something in common that we can divide by, and each of these terms has an n that we could divide by as well. In fact, since n cubed is our smallest exponent, they all have an n cubed that we could divide by. The number we could divide them by is not 2. I mean, yes, we can divide them all by 2, but we want to pick the biggest number, which would be 6, I believe. 6, and then n cubed, and in our parentheses, we're going to write what's left over if I divide each of these by 6n cubed. Or another way of thinking of it is 6n cubed times what gives me 24n cubed, because we're doing the opposite of distributing here. So that would have to be just a 4, because 6 times 4 is 24, and n cubed times nothing is n cubed. Like, there's not something that would change the n cubed. Alright, so let's come up with the middle term. 6n cubed times what gives me negative 18n to the 4th. Well, I need a negative, I need a times by 3, and I need an n. And then 6n cubed times what gives me negative 48n to the 9th. That would be negative 8n to the 6th. And so this should be my answer. The really great thing about factoring, in my opinion, is for the most part people seem to think multiplying polynomials is pretty easy. Like, the distributive property here is not that bad, so you can really easily go through here and check your answer and make sure that you've done it right. Now, the flaw to this is that if your brain made a mistake the first time, like in multiplication or some other sort of thing like that, it's probably going to make the same mistake, or there's a good chance that it'll make the same mistake the second time through. So do keep that in mind. It's not perfect, but it is better than not checking. Number 2 is the same instructions. We want to factor out the greatest common factor. Whether or not, by the way, we factor out a negative on these is kind of up to us. If the majority of them are negative, like they are in both of these, you're perfectly welcome to take out a negative, even though not all of them are. But if all of them are, you absolutely do want to take the negative out, because then the negative is in common for all of them. Here it would be optional. I could either do 4r, and I can only take out an r since this has just a single r. Either want to take out 4r, or I could actually take out negative 4r. I have options here. So 4r times what gives me negative 8r to the 6th? That would be a negative, a 2, and an r to the 5th. 4r times what gives me 16r squared. That would be 4r. And 4r times what gives me negative 20r. That would be negative 5. It should end up, when you're factoring out the greatest common factor, one of your terms shouldn't have a variable, unless you have something that mixes up a bunch of variables together. Like if there's only a single variable like x or a single letter like n or r, then one of them shouldn't have one. Otherwise, you didn't take out as many as you could have. If instead we took out a negative 4r, what that would do is it would change the signs. If I have negative 4r here and this was negative 8r to the 6th, that would make it positive 2r to the 5th. And then this would make it negative 4r and positive 5. And so either of those answers is perfectly acceptable. It would be whichever one you ended up basically deciding to put. Totally up to you. And so on our flowchart, our top priority was to factor out the greatest common factor. Conveniently, the instructions told me that I should factor out the greatest common factor. So voila, that's what we did. Now, we could technically try to factor the inside of the parentheses if we really wanted to, but the fact that we have these randomly weird higher power variables makes that super unlikely for us to be able to factor. We would need those to be an n squared or an r squared to even really warrant us trying to factor them. Now, this next section says a lovely set of instructions. It just says factor. And so here let's use our flowchart to figure this out. First step, check for greatest common factor. Pretty quickly, if you look through all 4 of these, you should go, okay, I don't see a greatest common factor. After that, we look at it and we say, how many terms does it have? Well, it's a trinomial. And trinomials in general, we split into 2 terms. If it's not greatest common factor, we're trying to put it in, not 2 terms, 2 parentheses, two factors like this in parentheses. And the idea is that we're doing the opposite of FOIL. So we would have something here, something here, something here, something here. That the first 2 terms multiplied together give me this a squared. The outside and the inside are what's giving me the 10a, and then the last and the last are giving me 21. So essentially we're splitting up this a squared here and here. And there's really only way to split up a squared, and that's a and a. At least there's only way for us to, one way to split it up so that the outside and inside together adds together to get something with an a. And so then that leaves us with the fact that this one and this one have to multiply together to get 21. So we're splitting this one up here and here. The only trouble is we want to split up 21 into 2 factors that also add to give us 10a. So it's helpful, depending on how good you are at thinking of factors in your head, to maybe make a list and always include 1 times whatever it is. You might be surprised how often that's the one you're looking for and also accidentally forgetting about. In this case, though, it is 3 and 7. And since we're multiplying to get a positive 21, then we're also adding to get 10. We want this to be a plus 3 and a plus 7. So that was a kind of long explanation for that. I'm just rewriting this to box it because I wrote a bunch of stuff over the other one. It doesn't matter which order you put this in. The 7 could go first and the 3 could go second because multiplication can happen in either order. But that's the idea. We're trying to split up 21 here and here, and we're trying to split up a squared here and here. We want to do it in such a way that the outer and the inner terms end up adding together to get the middle up here. So let's try that on some other problems here. Let's do p squared minus 15p plus 56. So what multiplies to get 56 that adds to get negative 15? So it may be that you think of it right off the bat, and that's great. It may be that it takes you some time, but you are able to think of it. It may be that you're just like, I have no idea what multiplies to get 56. If you're allowed to use a calculator, then go through methodically dividing things, and the things that give you decimals, don't write down. Like if I divide 3 into 56, it gives me a decimal, so I'm going to skip over 3, but I can do 4, and 4 into 56 gives me 14, and I can keep going. Now, those of you who already figured out what the factors are like, well, why go through all that trouble? It's the one you're supposed to think of with multiplication tables, 7 times 8. It's just funny the way our brains work, that if you immediately thought 2 times 28, your brain is going to likely get stuck on that and not want to think of other factors very easily without you making it by actually trying to divide numbers into 56. So we want to multiply to get a positive 56, but we want to add to get a negative 15p. And so that means that our 7 and our 8 both need to be negative. Because in order to multiply to get a positive, we either need 2 positives or 2 negatives, right? 7 times 8 equals 56, and negative 7 times negative 8 equals 56, because these negatives cancel out. But 7 plus 8 is 15, negative 7 minus 8 is negative 15. So we want those 2 negatives there. If I am trying to check my answers, I would do p times p and get p squared, p times negative 8, which is negative 8p, negative 7 times p, which is negative 7p. Those have to add together to get negative 15p. And then negative 7 times negative 8 gives me positive 56. So there's my answer. These other two down here, 5 and 6, are going to work the same way. So really it's just a question of, can you find the right factors, and also can you pick the right signs? We want to know what multiplies to get negative 18. So I'm not going to put negatives down here at first, even though a negative 18 means one of them needs to be negative. I'm just going to write them out. And then I'm going to look for, since one of them is supposed to be negative, I need what subtracts to get negative 7, not what adds to get negative 7. And so since 2 and 9 are 7 apart, that's what I'm going to go for. The question is, do I want it to be 2 minus 9, or do I want it to be 9 minus 2 in order to get negative 7? And so I want it to be a positive 2 and a minus 9. So x plus 2, x minus 9 is my answer. Number 6. Negative 7 is a nice prime number, which means there's only one set of factors that work, 1 and 7. So and since it's negative, one of them needs to be negative. Do I want it to be 1 minus 7, or do I want it to be 7 minus 1 to get the plus 6m in the middle? Well, I want it to be the second one. So I want m plus 7 and m minus 1. Alright, switching gears a little, we're going to factor things that have something in front of our x squared, or whatever our variable squared is. And so that is going to require us either to guess and check, which can be frustrating, or we're going to use something like the box method or slide and divide. Those are my two favorite, but I also know splitting the middle term is another one that people like. And you can find videos on all three of these methods. I have videos on box method and slide and divide, but not split the middle term. Alright, so for the box method, what you start off doing is multiply the first term and the last term's coefficient. So 5 times negative 28 is a number, 140, negative 140. And what we want to do is we want to pick factors of negative 140 that are going to add to give me negative 31. Now 140 is a big number, and since it's a comparatively small number, 31, it's probably something that's kind of a low down on my list of factors. So 1 goes in, 2 goes in, 4 goes in, 35. Actually, I take that back. That didn't take very long. My bad. 4 times 35 gives us 140, and if we subtract them, we get negative 31. So do I want 4 minus 35, or do I want 35 minus 4? I want it to be negative, so I want to do 4 minus 35. So here's where the box comes in. We're going to make ourselves what looks like a Punnett square. I apologize for it being kind of, tilted. That was not intentional. So what we do is we fill in this box in a particular way. We put the first term, 5p squared, in the top left. We take the last term, negative 28, and we put it in the bottom right. And then we take our numbers we came up with here, and we put them together with a p, because we're trying to add to get negative 31p. We put those in these other two boxes. It doesn't matter which one you put in which box. It just matters that they both have a p. And then we are going to look at the top two and the bottom two, the left two and the right two, and actually look for greatest common factors. So for instance, I'm going to look here and say, what's the greatest common factor of 5p squared and 4p? It would be just 1p. So I'm going to write that over here on the side. And then I'm going to look at the bottom two. So this negative 35p and negative 28, what do those have in common? They have a 7, but not just a 7, that negative is also in common. And then I'm going to look at the top two. I don't know how well this is going to work. Very terribly. That was not helpful highlighting. I'm going to look at the left two, and I'm going to say they both have a 5 in common and they both have a p in common. They don't have a negative in common since they're both negative, so I'm going to put 5p up here. And then I'm going to look at these last two. I just won't bother with the highlighter this time. 4p and negative 28 have a 4 in common, but not a negative, so it'd be a plus 4. What we're doing here is getting our parentheses that we need. So 5p plus 4 is going to be 1 parentheses, and p minus 7 is going to be the other parentheses. And this right here would be our answer. It doesn't matter which order you put it in, and in fact, if you flipped around the 4p and the negative 35p in their spots here, then it would actually give you your sides would be switched as well. So it doesn't matter which order you put them in, as long as what's in the parentheses is together with other things that are supposed to be in parentheses. Like, it has to be 5p plus 4. It can't be 5p minus 7 or something like that. That wouldn't work. Now, if you have done a Punnett square in biology or whatever science class, then you've seen how you take the genes on the outside and you put them together to get what's on the inside, and that's really how we can check our answer. And so that makes it familiar and kind of easy to do. You'd say 5p times p gives us p squared, 4 times p gives us 4p, 5p times negative 7 gives us negative 35p, and 4 times negative 7 gives us negative 28. Voila! We have the right answer. How nice. And so I'll try to talk less on these next three and go through it just a little bit more quickly, since I explained a lot on that one. Really, I think in general the toughest thing on these problems, if you know which method you're supposed to be using, the toughest thing then is figuring out your factors. So here I've got 2 and 50, which add together to get 52. And since I'm multiplying to get a positive 100, I need to make them both negative for this to work. Negative 2 plus negative 50 gives me negative 52. I'm going to fill in the box. So 5k squared and 20, and then negative 2k and negative 50k. So I'm going to look at the top two here and say, well, they don't have a number in common. They have a k in common. Also, I've glossed over the fact on this section that none of these have a greatest common factor that we can take out. If we did, we would do that first. Like, if I could divide all of these by 5, it would be much easier to take out a 5 from all of them and then try to factor again than to go through the box method. Okay, so now negative 50k and 20, what they have in common is 10. And then I'm going to look at the left two and say they both have a 5 in common and a k in common. And then the right two, they both have a 2 in common. Now if I check my answer here, I have this wrong, because I have k and 2 multiplying together to get negative 2k. So where's that negative supposed to come from? So the trickiest part on the box method over other methods, in my opinion, is these two being negative makes both of these negative, and that's a thing that you have to remember. Okay, both of these diagonal ones being negative makes the 2 and the 10 negative. So this is 5k minus 2. That's a really terrible looking k. And then k minus 10. And that would be our answer. But that's only when the two diagonals are that they both change. And so really it's if the bottom left corner is negative, then this one has to be negative. If the top right corner is negative, this one has to be negative. Sometimes this bottom right one will be negative, and that will help you know which one to make negative. But not in this case where both of the diagonal ones were. Okay, on number 9, this is going to give us an annoyingly big number that subtracts to get us a annoyingly small number. So we do 10 times negative 24, which is negative 240. And you can list out all the factors, and if you do it methodically, one number at a time, it'll be the last one you get to, which is 15 times 16. Since we're trying to get a negative 1, that means we need to do negative 16 plus 15. So I'm going to make my box and put 10x squared in the top left, negative 24 in the bottom right, and then negative 16x and 15x. And then I'm going to look for my common factors. So between these two, it would be 2x, and the bottom two would be 3. The left two would be 5x, and the right two would be negative 8. And if you're ever having trouble coming up with what this greatest common factor is, but you didn't have trouble on the other one, remember 3 times negative 8 is supposed to equal negative 24. And 2x times this number is supposed to equal negative 16x. So you can kind of use that to not cheat, but reason it out differently. So this is our answer. Okay, number 10. And we have negative 100 again. Well, I guess it was positive before, but we have negative 100. We're trying to get 99. Well, we better use 1 and 100. And since we're trying to get positive 99, that's 100 minus 1. So let's make our box. My, that's a tall box. 10b squared, negative 10. And then 100b and negative 1b. I don't have to write the 1 there, but I did. Accept it. On top here, we've got 10b in common, and down here we just have a negative 1 in common. And if these weren't both negative and I didn't put a negative 1 here, I would still put a 1. Like if they don't have anything in common at all, you need to write a 1 out on the outside, like a positive 1 in that case. On the left side here, they don't have a number in common, but they both have b, and then 110 have a 10 in common. So b plus 10 and 10b minus 1 is our answer. So I actually have put, for this particular review for my students, I've tried to put some hints in because I do realize that it can be overwhelming to see all these different problems that just say factor and have no idea how to factor and how to pick it out. So this says use special patterns. Those are the patterns that that require us to use square roots. And if you look at the numbers we have here, all of these numbers are things we can square root. 25, 16, not the middle term, that won't be a square root, but n squared and 16 have square roots, 4n squared and 25, p squared and 9, they all have square roots. If also we look, none of them have a greatest common factor that we can take out, so we can't do that first. We just need to try to use those patterns. And so the difference in the two patterns is 2 terms splits up into 2 parentheses that are the same other than one being plus and one being minus. So that means that this 25x squared should split up into the square root here and the square root here. So 5x plus 4 and then 5x minus 4. Remember, if you multiply this out, it should give you what you started with. And if we do multiply it out, the outer and inner terms cancel, and that's why there's only 2 terms instead of 3. Let's skip down to 14. That's the other one with 2 terms. So that should work the same way, except this is a trick question because it has a plus sign. So the reason that 2 terms can give us 2 parentheses is because when we're foiling, we're multiplying to get something that adds to get 0. And it's a little tricky to tell that on 11, what we're multiplying together, that when we're adding gets us 0. You can get there if you really want to. But on 14, hopefully it'll make sense. What we're essentially trying to do is figure out what multiplies to get 9 that adds to get 0p, because that would be what our middle term is since there's not one. Well, you can't multiply 3 times negative 3 and get positive 9. But that's really the only thing that makes sense to try, because 3 minus 3 is 0, and 3 times 3 in general is 9. So 14 is actually not factorable. And another word we use to describe that is prime, which you're familiar with numbers probably, but we can also use that with polynomials. So that was on purpose that I threw this in here. It's the difference of 2 squares that factors, not just any 2 squares. The other pattern is called a perfect square trinomial, and so we've got a trinomial where the outside 2 terms will be perfect squares. The middle term, and this is something that is hard for Algebra 1 students to typically accept. The only thing we actually care about from the middle is the negative, assuming we know we're supposed to use the pattern. Now, the reason this works is because this is n and this is 4 if we square root, and the middle term is n times 4 times 2. And that will always be the case. So here, this is square root, so we get 5, we get 2n. This middle term, 20n, comes from 2n times 5 times 2. So 2n times 10, which is 20n. But in order for us to actually factor this out, we can do that by putting it in one parentheses with the squared and using the 2 square roots, n and 4, and the sign that we get here. This is n minus 4 with a squared on the outside. Now this one you could have just figured out yourself by saying, what multiplies to get 16 that adds to get negative 8? And you probably would have come up with negative 4 and negative 4. And then you could rewrite it like this so it looks fancy and like you used the pattern. But it's a little trickier on 13. Now you can use the box method on 13 if you're not feeling the whole special pattern thing. But if you know the special pattern, you know you're supposed to use it, you square root the outside 2 things and get 2n and 5, and then you look at this sign in the middle to tell you this should be a plus. And that's our answer. So the special patterns, I think, are really one of the hardest parts for our young Algebra 1 minds, or mathematically young minds, to kind of grasp. But it's important that we see it now, so that then when we see it again later, it'll hopefully make sense faster. My favorite type of factoring, factor by grouping. So one of my reasons for it being my favorite is because it's obvious. It's the only thing you can do with 4 terms other than greatest common factor. So after you've glanced through and checked that there's not a greatest common factor, you want to look at the first 2 terms and the last 2 terms and treat those as like 2 separate problems. What does 16n cubed and negative 12n squared have in common that you can take out, which is 4n squared? And what happens when you take that out? You would get 4n minus 3. And then you look at the second 2 and you say, what do they have in common? They have a 5 in common. When you take it out, you get 4n minus 3. Oh wait, those are the same. And that's supposed to happen. If that doesn't happen and you've been told to factor by grouping, then you've done something wrong. If you're somewhere in your math class and you don't know if it factors by grouping, there's a possibility it doesn't factor. Well, if those don't match, then it doesn't factor at all and is prime. well, sort, yeah, let's just move on. Okay, so 4n minus 3 being in common here means that I can take out that 4n minus 3. And when I take out that 4n minus 3, I'm left with 4n squared plus 5. And so what we can do is we can split that into two parentheses like this. And if you FOIL this out, or distributive property, you get this. And you don't even actually really have to try that hard. You can do it in your head. 4n times 4n squared gives us 16n cubed. 4n times 5 gives us 20n. Negative 3 times 4n squared gives us negative 12n squared. Negative 3 times 5 gives us negative 15. Voila! So let's do the same thing on 16. No greatest common factor here. So there's a 3p squared in common, which leaves us with 3p plus, well, wait, I'm taking out 3p squared, but this is 3p squared. Make sure you put a 1 here, because this has to distribute back and give us this term. And so not putting anything doesn't let that happen. And that's an easy mistake to make, and one that you should definitely try to avoid. The second two have a 5 in common, but in particular a negative 5. And so that will change these to positives when we write them, 3p plus 1. So we have a 3p plus 1 in common, and then we have 3p squared minus 5. And now we're going to get to a couple of trickier things, which if you're like, well, hasn't it all been tricky up till now, then I'm sorry to disappoint you. 17 and 18 say factor each completely. This will require more than one step. And that last sentence is my attempt to give you a hint at what does it mean to factor each completely. It's implying that you might factor one time and then still be able to do something else. So this is where our trick of looking for a greatest common factor is going to come in handy. And so I just do that kind of without thinking, so that I have to really make myself even mention it, as I've been trying to, but even failed at some in this video. We want to look at this and we want to go, oh, this all divides by something. And even if you just are like, well, I know it all divides by 2, that's helpful, because we should absolutely try to take out a common factor if there is one. But there's also something bigger than 2 that we could take out. We can actually take out 4. So I'm going to take out 4 and get x squared minus 12x plus 35. But now I need to check to see if this goes further. This is the same idea as when you have 24 and you factor this into 2 and 12, but if you're making a factor tree, you don't stop there. You keep going with the 12, and you keep going until you can't go any further. This on the inside of this parentheses is not prime, or maybe it is and we need to check that. So we have to look at this without the 4 there. Pretend the 4 isn't really there. I wonder if I can make this work. Okay, that 4 is not there. Let's pretend it's not there. We're going to bring it back later, hopefully without any sort of technology snafu. And let's think, how do I factor x squared minus 12x plus 35? It's a trinomial, so it's going to factor into 2 parentheses. It's a trinomial that 35 does not have a square root, so definitely 2 parentheses. And it doesn't have anything in front of this x squared, so we want to just say what multiplies to get 35, that adds to get negative 12. And so that's going to be a minus 7 and a minus 5. But you're not really allowed to just pretend like this. Well, that didn't work. That's fine. I can write it back again. Can I? Yes, please. All right. That 4 was out there, and now it still needs to be out there. What we've done is we've said this is equal to this. And so since this was 4 times x squared minus 12x plus 35, it now needs to be 4 times this set of parentheses. Now, just having a single 4 makes that work. You don't need to put a 4 in front of the other parentheses as well, because the way multiplication works, we only, we're multiplying this whole thing by 4, like there's an extra set of parentheses. We just don't actually need to put that extra set of parentheses in. So that's nice. So this is our answer. If you are checking your answer, what you would want to do is multiply these together first. I keep writing a line underneath and then erasing it. How silly of me. multiply these out first using FOIL or distributive property, and then distribute the 4. And that will get you back to the answer. Distributing this 4 into both of these parentheses is incorrect. You choose one to put it into, and then you could FOIL if that's the way you want to go about it. All right, 18. So they have something in common. They all can be divided by 5. It would be nice if it had been 10, but it's not. So we're going to say 2n squared plus 3n minus 70 divided by 5 is 14. Okay, so we took out a 5, so we factored, and that's one step. But now we've got a trinomial. It's not a perfect square trinomial because we don't have anything we can square root. And it has something in front of n squared, so we can't just use the easy split it straight into 2 parentheses sort of situation. That means guessing and checking or using the box method. So let's make ourselves a box. And let's put the 2n squared. Again, we're going to ignore the 5 and just let it hang out there. So 2n squared and negative 14 go here. 2 times negative 14 is negative 28. What multiplies to get negative 28, that adds to get 3. That would be a negative 4 and a plus 7. So I'm going to do negative 4n and plus 7n. And then continue with the box. And the tricky thing here, and I get why it's tricky, is that you're having to do 2 methods at the same time, and that can make you just all of a sudden forget how to do the box method, even though we did it just a few problems ago. So look back at what you did, notice that it's the same thing, and try to repeat those steps. That's the best advice I can give you. So that's 2n, that's 7. I don't have a ton of room up here. You can write it under the box and to the right of the box also as a way to organize. So this is 2n plus 7 and n minus 2. And we keep that 5 in front because we want our answer to multiply out to give us the original thing. And without that 5, it doesn't do that. All right. 19, 20, 21, and 22 ask, can the following trinomials be factored? So what we should do to figure out if they can be factored is try to factor them. And if it's possible to factor them, then we'd say yes. If it's not possible, we'd say no. Here's what I mean. If I try to factor this into 2 parentheses, that means I'm going to look for what multiplies to get negative 63. That adds to get 2p. And I know that that's what I want to do because there's 3 terms and there's no square roots. So let's think about 63. I'm going to skip down to 7 times 9. Okay, so 7 times 9 is 63. We want to make one of these negative, which is convenient because we want to subtract to get 2. So 9 minus 7 gives us 2. So yeah, we can factor this. P plus 9, P minus 7. Our answer is yes. On 20, when I start looking at 1 times 7, one of these needs to be negative, and I need to add those to get 7. Well, that's not something that's possible, because 1 minus 7 is negative 6, and negative 1 plus 7 is positive 6. Neither of those are 7. I'm out of options, so this is a no. It's not factorable. On 21 and 22, there's no greatest common factor, and actually, technically, if there was a greatest common factor, that would be considered factoring, so that would mean that we'd answer yes. But there's no greatest common factor, so we would have to use the box method in order for this to work. And so we don't have to do the whole box method, but we do need to start it. We need to say 3 times negative 6 and get negative 18. Is there anything that multiplies to get negative 18 that adds to get 1? Since remember there's that invisible 1 in front of P. So basically, do any of these subtract to give us 1? Our closest option is 3 and 6, and that doesn't work. So no, this doesn't factor. Sometimes it'll be that nice where it's like, well, no, none of those are even close to working. Every now and then you'll get a particularly mean set of numbers where if you could just change up the signs in a way that you shouldn't. Like if it's supposed to be two positives, but you are like, well, if I subtract them, I get that answer. You want to be careful about that. That's not a good thing to mess up on. Okay, 22. 2 and 18 make 36. Is there anything that multiplies to get 36 that adds to get negative 15? 3 and 12. Because I can do negative 3 and negative 12. And they multiply to get positive 36. And they add to get negative 15. So yes. I didn't have to do the whole box method to figure that out. I just had to get to the point where I knew the box method would work. Now, when you're doing this, if you're in a class where your teacher likes to give partial credit and you have a situation like this, either a section devoted to it, or maybe there's just a section where you're factoring and you know it's possible that some can't be factored. If all you write is no or not factorable and you literally have nothing else written down, there's a danger to that. And in this section, I guess there's also a danger to writing just yes without anything else. Because if I'm trying to assign you partial credit and you say it's no, but it's really yes, I have no idea where you went wrong. Whereas if you've made a list of factors, like what I did on 22, let's say I made this list of factors for 36, and I even continued it and did all of them, 4 and 9 and 6 and 6, but I accidentally said 3 times 11. Well, look, nothing works. So let's say we wrote no because of that. Well, as a teacher, I can look at that and I can say, well, your mistake is that you said 3 times 11 was 36 instead of 3 times 12. So you knew the process of how to do this and figure out the answer. You made a much simpler mistake than just not understanding the question. So your points taken off on that would possibly be less than if all you wrote was no. So just keep that in mind as you are deciding how much work to show on problems. You should always show as much as possible if you want the most points as possible. That's how that works. Okay, here we are, final section. Solve each equation by factoring. So we want to do the same thing we've been doing. We want to factor this equation, and then we want to solve. So our answer is going to end up being n equals or x equals or y equals or whatever our letter is. In order for us to solve by factoring, and in general this is going to be true for us with quadratic equations, whatever our method is, we want to get everything on one side of our equation. We want it to be in standard form. And we want the n squared or whatever squared term to be positive, if at all possible. So I'm going to subtract this 5 over to this side, like so. And this problem is a little bit unfortunate in that it actually cancels that out and leaves us with n squared plus 5n, and then that equals 0. If this had instead had a third number here, we would factor this as a trinomial. Since there's two terms, it's not a trinomial. Our only option is difference of two squares, which I can't do here. I don't have a difference. I don't have two squares. Or factoring out the greatest common factors. So let's look and see. Do these both have something I can take out? Yes, they do. And so now that it's factored, I go a step further than I have before on this review, and I say, what do I put here for n that would make this 0? What do I put here for n that would make this 0? Because in order for two things to multiply and get 0, one of them has to be 0. So it's like we're letting them take turns which one gets to be 0. Like how you take turns with your friends if you're a nice person. So what makes this n equal 0 is a 0. If I put 0 here, it makes this 0, it makes the whole thing 0. But here, what do I add to 5? Sorry, no. What plus 5 equals 0? Well, that's negative 5. And when we've been graphing, we've been talking about the super secret opposite society and vertex form, and you can see how there's some super secret opposite society happening here as well. It's n plus 5, but our answer actually ends up being a negative 5. Let's do the other one over here. Now it already equals 0, so that's nice, but what's not nice is there's no greatest common factor, which means we are going to need to do the box method. So as we're factoring, we want to ignore this equals 0, and after it's in our parentheses, we bring that back and finish solving. So in case you were accidentally going to multiply by 0 here, no, we want to do 9 times -4 and get -36. We are trying to subtract to get 9, so we want to use 3 and 12. We want to do 12 minus 3 to get a positive 9. So I'm going to make my box. And look at the top two and get 3x. Look at the bottom two, which is -1. The left two, which is 3x, and the right two, which is 4. So when we factor this, we get 3x minus 1 and 3x plus 4. And now we're going to do the same idea as the last one. We want to say what can we do to make this parentheses 0, and what can we do to make this parentheses equal 0. So it's not that we're trying to make x be 0. We're not plugging in 0. We're saying, how do I make this whole thing be 0? And the 3 in front makes this a lot harder than over here where there was nothing in front of n. Because now I would have to multiply something by 3 and then subtract 1 in order to get 0. And that's actually going to, spoiler alert, involve a fraction. The easiest way to do this is actually to separate these into two equations. 3x minus 1 equals 0 and 3x plus 4 equals 0. And then solve them like a good old two-step linear equation. So add the number that's not attached to x over to the other side, and then divide by what's in front of x. So our first answer is x equals 1/3. And if you squint and try really hard, you might be able to come up with some super secret opposite society here as well. On the second one, we're going to subtract 4 and get 3x equals -4. And then divide by 3 and get x equals -4/3. And that's it. That's the stuff that we do with factoring, at least as far as Algebra 1 goes. And this has been a long video. There's a lot to this. But with practice, a lot of it can come really easily. Really, from my perspective at least, whenever I have to do these things, my least favorite of these is when I have to go to the trouble of using the box method. But considering back whenever I was doing this in school, I didn't know there was this really cool box method or slide and divide or anything else. I just guessed and checked. Really, even the box method isn't that bad in the broad scheme of things. It just takes a little bit more work. So I hope you've enjoyed this review. Please feel free to subscribe, like, comment, and keep being awesome.